Physics and mathematics in our simulation and base reality. Speculation on differing physical laws in a simulated universe and the universality of mathematics. It has often been suggested that if our reality is, in fact, a simulation, the laws of physics we observe need not coincide with those of any base reality that might be hosting said simulation. This proposal takes on a variety of forms, ranging from popular science fiction depictions to serious philosophical inquiry. But the core idea is the same. Just as a video game creator can program any number of whimsical or realistic physics engines for a virtual world, so too could an advanced civilization design a simulated cosmos with whatever physical parameters it chooses. From the point of view of us, the simulated inhabitants, these parameters would appear consistent, universal, and inescapable, precisely because they are carefully maintained to feel that way. Yet underlying this proposition is a striking contrast between the mutability of physics, on the one hand, and the perceived constancy of mathematics, on the other. Many thinkers argue that while physics might be programmed to be any set of rules, mathematics is more fundamental, an abstract logical framework that holds true regardless of the universe in which it is applied. This essay aims to delve deeper into these speculations, exploring various angles of how and why the laws of physics might be different in a simulated environment, and whether math truly stands above all as a universal constant that transcends the specifics of any reality. The simulation hypothesis. A brief overview. To situate the discussion, it helps to outline the essence of the simulation hypothesis. In broad terms, it states that an advanced civilization, whether human or otherwise, might reach a level of technological sophistication that allows them to create highly detailed, self-contained universes running on computational substrates. These universes would be populated with simulated entities that may or may not develop consciousness or self-awareness. For the inhabitants inside the simulation, the system's rules, which we would call physics, would form the entire basis of their reality. They would make observations, formulate scientific theories, measure constants, and build technology without realizing that an outside entity had consciously programmed these fundamentals. From the perspective of the base reality's simulators, these laws of physics could be chosen. Perhaps they pick a certain speed limit for light, define how electrons behave, or shape the relationship between mass and energy. Or perhaps they replicate a subset of the laws from their own environment, but tweak certain constants for experimentation, or to see how life might emerge under different conditions. The point is that, in principle, if one can simulate an entire cosmos, it becomes plausible that these rules need not match the simulator's own environment. Physics as programmable parameters. A useful analogy is indeed a contemporary video game, albeit on a trivially smaller scale. A game developer might decide to build a world where gravity is half that of Earth's, so characters can leap impressively high. Or they might code in frictionless surfaces, instantaneous teleportation, or time manipulation. The internal logic of the game remains consistent. Objects fall at a certain rate, collisions follow certain rules. Yet those rules are wholly at the discretion of the developer. Scaling that idea up to a hypothetical cosmic level, advanced simulators could define the physics engine for our entire universe. As an example, what if the speed of light had been chosen as 300,000 kilometers, but in the base reality, it is 400,000 kilometers s, or takes a wholly different form? Similarly, universal constants like Planck's constant or the gravitational constant might be mere variables in an unimaginably large computational system. Our scientific pursuits, from Newton's laws to quantum field theory, would merely reflect the emergent results of these coded rules. They would appear so stable and mathematically tight because the system is meticulously designed to not betray its computational underpinnings. One might ask, if that's the case, why do these laws appear so profoundly elegant, consistent, and sometimes even inevitable to us? The answer might lie in the requirement that a well-functioning simulation must not appear contradictory to its inhabitants. If we, as simulated beings, were constantly running into glaring breaks in continuity, like sudden changes in physical constants or random violations of conservation laws, we might become suspicious. By ensuring the rules remain stable and consistent, the simulation's architects maintain a sense of immersion. As a corollary, the more stable and elegant the laws, the less we would suspect that they were artificially chosen. A range of possible variation. If physics can be anything, one might wonder, do the simulators face constraints of their own? Possibly yes. Even if advanced beings can define many aspects of the simulation's physics, They may rely on certain computational limitations or prefer certain frameworks for aesthetic, ethical, or practical reasons. For instance, maybe simulating stable complexity, like life, consciousness, or entire civilizational progress, requires a set of rules that encourage emergent structures, not immediate chaos. If they pick random or contradictory constants, the resulting universe might be too unstable or short-lived to harbor interesting phenomena. Hence, although in principle they could choose any rules, in practice they might select carefully, guided by a desire for complexity, longevity, or certain evolutionary processes. This subset of workable universes might be narrow enough that from the inside, it feels as if these laws are fundamental. Meanwhile, from the outside, there might be infinite possibilities for how to code them. Why we don't see the cracks. If the laws of physics were indeed artificially set, we might wonder why we see no direct evidence of their artificiality. Some propose that phenomena we don't fully understand, like quantum uncertainty, dark matter, or certain cosmic coincidences, could be subtle hints of a coded reality. This is by no means a conclusive claim, but for the sake of speculation, it's possible that small anomalies or glitches do exist yet are interpreted as natural mysteries by scientists. Alternatively, the simulation could be robust enough to hide any cracks behind an elaborate set of processes that respond dynamically, patching any emergent errors. In advanced computational terms, the system could debut itself in real time if certain anomalies threaten the coherence of the world. Another layer of speculation is that if the base reality's laws differ drastically, we might never find direct conceptual overlap. We could attempt to unify physics in our universe, a theory of everything, only to be stumped by a fundamental mismatch, like pushing on a locked door that leads nowhere. But to us, that locked door might just appear as a horizon of scientific understanding, not evidence of an external programmer. Mathematics is a deeper constant. Opposite the viewpoint that physics could be anything is the notion that mathematics is more fundamental. Many philosophers, mathematicians, and scientists hold that mathematics is discovered, not invented, that it's a reflection of deeper truths about logic, quantity, and structure. Under this stance, 11222 is not just a cultural artifact. It is a statement about how units accumulate that would hold in any coherent reality. If an advanced simulator tried to code a universe where 11HA3 in an absolute sense, they would run into contradictions, or be forced to systematically manipulate the definitions to an absurd degree. The idea is that math, being an abstract set of relationships, is not dependent on the physical parameters of a given cosmos, but on underlying logical consistency. Within our own science, mathematics is used to describe physical phenomena, but the mathematical statements themselves, like the prime number theorem or the concept of infinity in set theory, do not rely on the specifics of how gravity or electromagnetism function. The claim, then, is that mathematics is just as true in the base reality as it is in the simulation, because mathematics describes structures and logical relationships that exist independently of any physical instantiation. The hypothetical simulators cannot simply declare 2222T5 without unraveling the logical scaffolding of the simulation's internal consistency. How simulated mathematics could appear the same? If an advanced simulator sought to replicate a world akin to ours, they might implement physical laws that align with the standard mathematics we know. Even if they're able to override or manipulate certain things, they might keep the mathematics consistent. For instance, the simulation might allow for advanced geometry or fractal expansions, but the core relationships of numbers, sets, and proofs remain the same. Indeed, it might be simpler for them to rely on actual mathematical truths rather than conjuring up an entirely new logic system. Moreover, a stable, consistent mathematics is presumably beneficial for the emergent simulated minds to form reasoned scientific systems, fueling the simulator's curiosity about how those minds might develop. However, one might also imagine a scenario where the simulators tamper with logic or set theory. If that were possible, the inhabitants might end up with a bizarre or contradictory mathematics that still works within the system's illusions. Yet this notion tends to lead to philosophical paradoxes or an unrecognizable environment, less straightforward for meaningful emergent complexity. Thus, the simpler assumption is that mathematics remains universal and consistent, whether we exist in a base reality or in a nested simulation. Could the base reality's mathematics differ? Another line of speculation. Might the base reality's inhabitants have a different understanding of mathematics, Or might they have discovered additional structures or axioms that yield different outcomes than ours? For instance, could they have built expansions to logic that we have not yet conceived, or found that certain conceptual sets are invalid in their domain? This is an open question. Typically, the stance that mathematics is universal doesn't preclude discovering new mathematical truths. It just suggests that once discovered, those truths hold consistently. If the base reality had advanced mathematics that we have yet to discover, that wouldn't necessarily conflict with the notion that mathematics is universal. It might simply indicate they're further along. In other words, if they decided to feed only a subset of their mathematical knowledge into our simulation, we might be on track to discover it step by step. The potential remains that if we advanced enough in the simulation, we might glean glimpses of the broader structure the simulators know, but that might require enormous leaps we've yet to make. Philosophical and existential implications. The difference between variable physics and fixed mathematics has existential ramifications. For instance, it might be unsettling for many to think that constants we revere, like the gravitational constant or the speed of light, could be illusions. Are our efforts to unify quantum mechanics and general relativity ultimately attempts to decode a set of artificially coherent rules? Could the theory of everything be, in fact, the theory of everything in this code? Simultaneously, there is an oddly comforting perspective in that mathematics would remain consistent. Even if we inhabit a simulation, our fundamental logic, arithmetic, and geometry still reflect something genuinely real, or at least something that transcends any single universe's physical laws. That is, solving a difficult proof in number theory might yield truths that are as valid in the base reality as they are for us, bridging the gap between programmed world and real world. Potential evidence or tests. One might wonder if there could be empirical ways to test the idea that physics is just code. Various proposals have cropped up, from searching for rounding errors in cosmic rays to detecting anomalies in certain quantum experiments. While none have definitively demonstrated we live in a simulation, it's the sort of question that's notoriously difficult to test. If the simulator is advanced enough, it might design the physics engine to never betray such computational underpinnings in publicly observable ways. Math, on the other hand, is not discovered by measuring cosmic rays. It emerges from logical deduction, proofs, and mental constructs. So testing whether mathematics is universal might be simpler in principle. We see that logic and arithmetic hold across countless applications. If it were to break, that might be the closest hint we'd ever get that we're in a scenario where fundamental logic isn't stable. But so far, no matter how advanced our scientific or computational ventures become, mathematics remains internally consistent in every domain we apply it to, reinforcing the notion that it's deeper than any single physical instantiation. Cultural or religious parallels. Interestingly, some cultural or religious notions parallel the discussion about variable physical laws versus stable cosmic truths. Many traditions have posited that the world we see is ephemeral, changeable, or illusory, while certain transcendent truths, sometimes moral or spiritual, are eternal and universal. Replace moral or spiritual truths with mathematical truths, and the parallel is evident. A dynamic physical realm overshadowed by an unchanging layer of reality or logic that undergirds everything. While this is not a one-to-one match to the simulation argument, it highlights that humans have long been intrigued by the possibility that the sensible world might be ephemeral. The difference in modern times is framing it in computational terms. Intangible higher truths become mathematics, and ephemeral material illusions become code-based physics. It's yet another lens by which these ideas can be re-explored. Social and ethical ramifications. If indeed our physics is subject to an external programmer, one might ask how that affects ethics, morality, or how we structure society. Perhaps it doesn't. Practically, even if we suspect we live in a curated environment, our day-to-day decisions still operate on the basis of the apparent rules. Gravity still works. We still need food, water, shelter. On the social front, humans, or any conscious beings, have historically derived moral frameworks from empathy, cooperation, or cultural evolution, not necessarily from the fundamental constants of physics. Knowing that G or C might be artificially set might do little to change everyday morality. However, if the knowledge were widespread, some might adopt an anything-goes attitude. If it's all code, why does it matter what we do? Yet, as with any advanced game or environment, harm done to simulated beings might still be harm from the perspective of those beings. Whether or not the environment is code, the experiences of joy, suffering, love, or fear remain real to the participants. So moral systems likely would remain crucial, as they define how we treat one another within whatever environment we occupy. Moreover, if we accept that mathematics is universal, does that impose a cosmic sense of right or wrong? Probably not. While math can unify truths about quantity and logic, it does not automatically yield moral guidelines. So the core moral debates remain, regardless of whether we're in base reality or a nested simulation. Could our universe evolve into a different physics? A tangential idea emerges. If the simulators can patch or update the system, might the laws of physics evolve over time from our perspective? For instance, a new patch might change the gravitational constant slightly, or adjust the vacuum energy. Would we notice? Possibly. We might interpret it as a cosmic shift or an unexplained phenomena. But if the simulators are adept at weaving the new laws in seamlessly, we might simply rationalize it as a natural cosmic phase transition. This underscores the idea that physics is not guaranteed to be static if it's coded. But thus far, from human recorded history, we see no dramatic changes. Our measured constants remain consistent. So either no patch has been introduced, or it's done too subtly for us to detect. Mathematically, though, could the simulators patch a new system of logic? That scenario becomes more abstract. If they tried rewriting 222p5 at a base computational level, they'd also have to rewrite all the emergent layers that rely on arithmetic. Potentially, everything would break or require enormous illusions to maintain coherence. And the complexity of such a patch might be beyond even advanced simulators, so maybe they do not bother. Alternatively, in a grand sense, mathematics is not something you can just patch out without unraveling the entire conceptual space upon which the simulation is built. Convergence of theoretical insights. Interestingly, some frontiers of theoretical physics, like efforts to discover a final unifying theory, start to sound reminiscent of code analysis. We keep looking for a hidden algorithm or a generating principle that yields the known constants. This is reminiscent of the notion that a well-coded simulation might have a master equation or function from which everything else emerges. Meanwhile, mathematicians keep discovering new structures, many of which appear to have no direct physical analog, but might exist purely in the realm of abstract logic. If the simulation argument holds, maybe these apparently useless branches of math are glimpses of broader logic known in the base reality, but not directly manifested in our simulated environment. In effect, the pursuit of deeper physics or pure math can be seen as either attempting to read the source code of our simulation, in the case of theoretical physics, exploring the universal language that underlies any possible cosmos, in the case of mathematics. Conclusion: a realm of possibility. From a speculative standpoint, it seems entirely plausible that the physical laws we treat as absolute might be as flexible as any set of instructions in a cosmic level program. Our measured constants, laws, and emergent phenomena could differ drastically from the environment in which the hypothetical simulators reside. Meanwhile, mathematics is widely regarded as more fundamental, an enduring tapestry of logical relationships that remains valid regardless of how or where it's applied. In a scenario where advanced beings have created our universe as a nested environment, one can see how they might meticulously choose or even experiment with physical parameters, curious to see how life and civilizations develop. But that does not necessarily extend to them rewriting mathematics at will, because logic itself might be too universal, too woven into the fabric of rational consistency, to easily replace it. If 2 didn't equal 4, the entire conceptual framework might unravel, preventing any stable emergent structure or conscious reasoning from forming. Hence, within the speculation that we live in a simulation, the difference is, physics might be arbitrary and different from the base reality, while mathematics is presumably universal and recognized by any intelligence, be it those who coded our cosmos or ourselves trying to decode our cosmos or ourselves. This viewpoint neither confirms nor denies that we are, in fact, living in such a simulation, but it illuminates how the tension between changeable physical laws and enduring mathematical truths can be understood if we imagine a reality built on code. In the end, whether or not we accept the simulation hypothesis, the notion that physics could be pre-programmed while math remains fundamental offers a thought-provoking lens. It invites reflection on how we perceive the nature of our universe and the bedrock upon which it rests. And it reminds us that while scientific inquiry can reveal consistent laws within our domain, there might forever be the tantalizing possibility that these laws are but one instance in an infinite sea of potential rule sets, while mathematics, in some sense, stands outside, bridging the gap between realities.